Alright, this lecture deals with exponential and logarithmic functions. It's a pretty heavy lecture, so I'm probably going to have to use several parts to get it all in. And also, sort of relying on you to remember the basic properties of exponents and logarithms. I'll see what I can do as far as reminding you of them. But in the meantime, we'll work with what we have. What I have here is a graph of the function y equals e to the x. I want to remind you of some of the properties of this thing. So we'll draw on this graph as we move along, but let's take a look at some of the things that you should probably remember about them. The y-intercept is 0, 1. Other than that, it has no other intercepts. We already know it's differentiable. In fact, it's differentiable for any real number. The derivative of e to the x is e to the x. It's perhaps the best function to take the derivative of any function there is. The function is always increasing. You can tell as you go from left to right. If you trace along the x-axis with your hand and go from left to right, the y values continually go up and up and up. And in fact, they increase fairly rapidly after you get past the y-axis. The function is continuous everywhere. Well, since it's differentiable everywhere, that automatically means it's continuous everywhere. E to the x goes to infinity as x goes to infinity. But if you look at the other side, as x goes to negative infinity, you'll see that the graph gets closer and closer and closer to the x-axis, but it doesn't cross it. That's what we call the y-axis, or the x-axis, as a horizontal asymptote. The limit as x goes to negative infinity of e to the x is 0. As I mentioned, 0, 1 is the only intercept. And it just happens to be a y-intercept. As I mentioned, y equals 0 is a horizontal asymptote. Now, what I want to do is define an inverse function. If you look up at the graph of f of x equal e to the x, it's not only a function since it passes the vertical line test, but it also passes the horizontal line test. So what that means, we call such functions one-to-one. What that means is that for each x value, there's a y value. Well, we know that just because it's a function. But for each y value, there was only one x value it went to it. That's why we call it one-to-one. So this function passes the horizontal line test. It's one-to-one, therefore it has an inverse. Now, I can tell you some things about the inverse just based on the information I have from the original graph. Let's see. The differentiable, the increasing, the continuous, I can't really get that right off the bat, but I can get anything that deals with x and y values because an inverse function simply switches x and y values, because the inverse is supposed to take y's back to the x's from where they came. The first thing I'm looking at then is the limit as x goes to infinity of e to the x equals infinity. Now all you have to do to get a handle on the inverse is switch anywhere you see an x with a y. So this first one then can be written as the limit as y goes to infinity of f inverse of y equals infinity. e to the x is the f function, so f inverse, of course, is what we're dealing with now. In the second one, I can do the same thing. The limit is y goes to negative infinity, e to the y, and I'm sorry, f inverse of y equals 0. Now then we have 0, 1 was a y-intercept. So, and it was the only intercept. That means the inverse will only have one intercept, but it won't be a y-intercept, it'll be an x-intercept. If the original had a y-intercept of 0, 1, the inverse has an x-intercept of 1, 0. If the original function has a horizontal asymptote of y equals 0, the inverse function has a vertical asymptote of x equal to 0. Now here I have a graph of the inverse function. You can see that the x-intercept is like I said. This function, you probably know, is referred to as the natural logarithm of x, ln for short. So you can see it does. I mean, if I were to flip this graph around, especially if I were to reflect it about the line y equal x, I would get the original function. We'll do that in a minute, but right now let's catalog a few of the properties of the natural logarithm of x. We have those. If you look, as y goes to infinity, that means the y values are increasing, then the x values go to infinity. Remember, you're always flipping x and y. Similarly, if y is going to negative infinity, this function has x values that are going to 0. You can see that the line x equals 0 acts as a vertical asymptote, just as was mentioned before. In fact, the domain of the original function is negative infinity to infinity, and its range is 0 to infinity, not including 0, because the graph does not touch, the graph of the original function, e to the x, does not touch the x-axis, so its range is 0 to infinity, not including 0. When you go to document the inverse function, you simply flip those two things. Domain refers to x in the original function, so it corresponds to y values in the inverse function. So here, it's not the domain that's negative infinity to infinity, but it's the range that is negative infinity to infinity. Before, the range was 0 to infinity, and now the domain is 0 to infinity on the inverse function. And you can see that based on the y values, they obviously go to negative infinity and up to infinity. Here I've graphed e to the x and ln of x on the same axes, and the line y equals x. That's the one that's dashed in the middle, that goes through the middle of this graph. So f of x is e to the x, the inverse function is ln of x, and they are what you'd call reflections about the line y equals x. It's as if that line were a mirror, and they're mirrored across that. That's why whenever you take a point xy on the original function, let's say 0, 1, flip the numbers and get 1, 0 on the inverse. You can see I'm sort of drilling them in there. They have other, you could do it for anything. Just pick something to make sure that its exact inverse is on the other thing. Let me pick something around x is a little more than 1 and y is equal to 3 in that dot there. X a little more than 1, y is 3. So now when I go to x equals 3, I do get a y that's a little bit more than 1, just like in the previous picture. It's also the reason why the horizontal asymptote, the y equals 0 of the original function, changes to a vertical asymptote, because a horizontal asymptote has an equation like y equals some number. A vertical asymptote has an equation like x equals some number. So if you're always going to be switching x and y, it makes perfect sense that a horizontal asymptote would correspond to a vertical asymptote on the inverse. So in fact, if you take a horizontal line and flip it about the line y equals x, it becomes vertical. Notice both functions do go to infinity as x goes to infinity. It's just that e to the x does it way faster than ln of x does. The best I can do with the limit as x goes to 0 is to do it from the right side, because the logarithm is not defined for numbers that are less than or equal to 0. Non-negative number, or only positive numbers really. And since e to the x does not touch the line y equals 0, the inverse function does not touch the line x equals 0. Now, one of the basic relationships you had with ln of x and e to the y is given right there. ln x equals y if and only if x equals e to the y. Now, basically in general, if I take f composed with f inverse, I get the result of x. Of course, f has to be defined for each of those f inverse of x's. And the same thing happens if I do f inverse of f of x, I get x. That's inverse undoes the original function. So let's set that up according to f of x equals e to the x, f inverse x equals ln of x, and let's rewrite those two equations I did before. So f of f inverse of x is supposed to equal x. So the f was an e to the, and f inverse was ln of x. That equals x. That's only good for positive values of x, because the first thing I have to do is make the x pass through the natural logarithm. So it's good for all positive x. On the other hand, we have f inverse of f of x is also equal to x. So then the f inverse was ln, so I'll replace f inverse with ln, and f was e to the x. Now here you can take any number as an exponent, so this equation is actually true for all real numbers x. That's what that little weird looking r is. It's all real numbers. And this is typical, because unless they were both had domains of negative infinity to infinity, ranges of negative infinity to infinity, it's quite possible that you could have a situation like this where one is more limited than the other. As a final note, you could drop the parentheses. That seems to be a popular thing to do when you're talking about natural log. So you can write ln of parenthesis e to the x or ln of e to the x. Now, let me try to get a derivative of this thing. If y equals ln of x, then what is dy over dx? Well, let's go back. Y equals ln of x. What does that mean between x and y? It means that e to the y equals x. Now I'm going to take the derivative with respect to x of both sides of this equation. The derivative of e to the y is e to the y, but then you have to use the chain rule and multiply it by dy over dx. And actually, wait, let me change it just to y prime. It's a little bit easier with notation like that. and the other side is equal to 1. And now I'll divide by e to the y and get y prime equals 1 over e to the y. But e to the y is equal to x. So I can replace e to the y with x. And so there's my derivative rule for the natural logarithm of x. The derivative is 1 over x. Now check this out. Suppose I allow y to equal the natural log of the absolute value of x. Now once you put absolute value around the x, you're doing the absolute value before you take its natural logarithm. So when I have absolute value there, I'm going to extend the domain to all real numbers except 0. That's important because we'll be using it for some other activities besides just taking a straight up derivative. Notice the symmetry of the graph is the same on the left or right side of the y-axis. All right, when x is negative, the absolute value of x equals negative x. That's how it makes it positive. So, if I have y equals the natural log of negative x, then y prime equals 1 over negative x. You know, negative x is positive, so it's in the domain of natural log. But I have to take the derivative of what was inside the parentheses, which was negative x. Now let me clean it up a little bit. I have 1 over negative x times negative 1. The negatives cancel and I get 1 over x. So this is nice. This is a sort of a getting something for nothing kind of a deal. The derivative of the natural log of the absolute value of x is actually equal to 1 over x also. This is better than the original one because you are allowing the domain to go from negative infinity to infinity, but just taking out x equals 0. Whereas the other one was only had half the size of a domain. So this will allow you to do more things. Let's do some examples. Let's do y equals ln of 3x squared plus 1. When you take the derivative of y, first thing you do, since you're dealing with an ln function, is to take 1 over the stuff inside of the parentheses. So I'm going to take 1 over 3x squared plus 1. Now according to the chain rule, now I have to take the derivative of the stuff that was inside the parentheses, the inner function. So I get the derivative with respect to x of 3x squared plus 1. Now let me clean it up a little bit. 1 over 3x squared plus 1, increase that vinculum a little bit, times 6x. And there's no reason really to simplify any further. I'll do simplifying only if I'm going to use my results in a future calculation. But for these, where the answer is where you're trying to get to, just leave it as it is. Let's complicate things a little bit here. Y equals the natural logarithm of tangent of x. dy over dx equals, first thing you do is take 1 over tangent of x times the derivative of tangent of x. And so I end up with 1 over tangent of x times secant squared of x. It very well may be possibly true that this simplifies, and I believe it simplifies a lot, but I'm not using it for a future calculation, so I'll end there. I'm happy with my answer. You know, you can get cosine, you can break it down to cosines and sines and do a bunch of simplifying, etc., etc., etc. Here I'm going to do something more complicated. Y equals the natural log of 1 minus 3x plus x cubed, all of that over the square root of x. Now this is the cool thing about logarithms, and the fact that the derivative of the logarithm is the same, well, the derivative of the logarithm of x is the same as the derivative of the logarithm of the absolute value of x. That means that I can ignore a lot of domain problems simply because, at least in so long as when I take the derivative. So if I had absolute values around everything on the inside of those parentheses, I would with no problem at all be able to break this up just like you have with logarithms before. Division sign corresponds to a subtraction of logarithms. Then I can take derivatives as I normally do, so I'd get 1 over 1 minus 3x plus x cubed times the derivative of 1 minus 3x plus x cubed. And the other piece, I just realized that I had a y where I should have had an x. But better than that, the square root of x is x to the 1/2 power. So I'm going to put a 1/2 in front. So I have minus 1 over 2x. The derivative of ln of x is 1 over x. All I got to do now is take the derivative of 1 minus 3x plus x cubed, and I'm going to get negative 3 plus 3x squared. And so there you have it, complete solution. I'm happy with that. Don't worry about doing any simplifying. And I explained that because the derivative of the function is the same as the derivative of the absolute value of the function inside, that's why I could do all this business. Because I've always been worried about taking natural value or breaking things up and you changing the domain. You don't have to worry about that in these problems. And that's all because it doesn't matter whether the x's are positive or not. At some point you could put absolute values around everything and all of this stuff works out perfectly. Next, suppose you have a number b that's greater than 0 and not equal to 1. I want to look at exponential functions with a base perhaps not necessarily equal to e. So what is b to the x look like as a graph? We'll start with y equals b to the x. I'm sure you've seen these before, so I'm just going to sort of do a quick reminder of this. You have a decreasing function. It still goes through 0, 1 in the case where b is a positive number but still less than 1. On the other hand, if b is greater than 1, you'll have a graph that looks very much like e to the x. In fact, it goes through 0, 1 just like e to the x does, except now it's an increasing function. So those are the two situations that you have to work with. Now let me see if I can figure out the derivative of this thing. I think I'll start with y equals b to the x, and I want to determine y prime. So I'm going to take the natural log of both sides. Take the natural log of y equals the natural log of b to the x. I can take the x out front of the natural log because the b is a positive number, so it's defined. Let me change that y to something reasonable. Okay. Now let me take the derivative with respect to x of both sides. So on the left, you'll get 1 over y times y prime, because you have to use the chain rule. On the right, ln of b is just a number, so all you're going to get is ln of b. The derivative of x will be 1. So that takes care of that. Then I'm going to have y prime, or dy over dx, equals y times ln of b. Now y is equal to b to the x, so I'm going to change this to b to the x ln of b. So the derivative of b to the x equals b to the x ln of b. Notice it's different from our power rule from before. This is a little bit different because the exponent is variable, but the base is fixed or constant. It's not quite what we were doing before. The power rule that we used before had a base that was a variable, but an exponent that was a number. Here we have a number as a base and an exponent that's variable. So that equation, the power rule, does not work. Make a note of this. That is not true. The thing I have boxed is the correct equation. The thing that I do not have boxed, or the part that I have the slash through, that stuff, you need to make it a point to yourself to know that that is an untrue statement. That's something that catches a lot of students, especially if they're not studying in some depth. Let me do some examples. Y equals 2 to the x squared. So dy over dx, the first thing you're going to get is 2 to the x squared ln 2. Because the base is 2. The exponent is variable, so you get 2 to the x squared ln 2. Now, though, the x squared is like the inner function, so I have to take the derivative of x squared. So I'll take d over dx of x squared. So I get 2 to the x squared ln of 2 times 2x. And that's perfectly fine as an answer. As you know, you don't have to simplify. If you want to be cool, you can combine that 2, the 2 in front of the 2x, that's 2 to the 1 power. I can combine that 2 with the 2 to the x squared and get 2 to the x squared plus 1. Move the x out front. I guess that looks a little bit better. Either one of those is fine. You don't feel compelled to simplify whatsoever. All I did was combine things that had the same base, which was a 2. Now another example. Y equals pi to the x. Here we have a number as a base and a variable exponent. So dy over dx equals pi to the x ln pi. Now let's take a look at x to the pi. Here you've got a variable base, but a number as an exponent. So this follows the familiar power rule. Nothing's fancy here. You're just going to have dy over dx will equal pi x to the pi minus 1. Except we haven't really dealt with irrational numbers. We have a power rule for rational numbers. So what do we do in this case? Well, notice that e to the ln of x is x. So e to the ln of x to the pi is x to the pi. This is going to allow me to deal with exponents that are different from rational numbers. Do you see the pi? I can pull the pi out front of the ln. Now let me take the derivative of both sides with respect to x. So when I take the derivative of the left side, I'm going to have e to all that stuff, but then the derivative of the exponent. So I have d over dx, e to the pi ln of x, but then take the derivative of pi ln of x after I do the e part. I'm not going to evaluate the right side yet. In fact, that's what I'm trying to determine the formula for. On the left, I get e to the pi ln of x, because e to the x, derivative of e to the x is e to the x. But then take the derivative of the exponent, which is pi ln of x. Leave the other side alone because that is the formula I'm trying to determine. Good. Now I'm going to replace e to the pi ln of x with just x to the pi. D over dx pi ln of x is just pi over x because pi is a number and ln of x has a derivative that is 1 over x. So here is my formula for the derivative of x to the pi. Now I can simplify by canceling out an x with the exponent to make that x to the pi minus 1 times pi. So here's my formula. D over dx x to the pi equals pi x to the pi minus 1. The whole point of this is that now the entire thing, no matter what kind of number you have as an exponent, if you have a variable base, the exponent rule works. The power rule works for all of them. Remember, except 0. 0 is sort of a strange thing that we have to handle separately. Now let me move on. Hopefully you can see that e to the ln x to the p is equal to x to the p. I'm going to do essentially the same thing I did before. I'm going to deal with x as being positive when I'm dealing with these powers. I'm going to take the derivative of both sides after I take the p and put it in front of ln of x. Okay, here we go. d over dx of e to the p ln of x equals d over dx of x to the p. And the left side, as before, you're going to have e to the p ln of x times the derivative of p ln of x. This is going exactly like p is a great letter to choose because pi is the letter p in Greek. So I think I'm going to change that e to the p over x back to x to the p. So you're referencing the original function and its derivative. And then the derivative of the rest of the stuff is going to just be p over x because p is a number and the derivative of ln of x is 1 over x. So I have a formula for x to the p where p is any real number except 0. So d over dx x to the p equals p x to the p minus 1 for any real number p. Except p equals 0. I keep forgetting to write that little piece, but write it down yourself. Except p equals 0. Do not take that for p equals 0. If p equals 0, the function is just x to the 0, and we treat that as just being 1.